Hello again, this is Masa-aki Haga. Today I will discuss about electrified interface between electrode and modified catalyst. In the last lecture, I discussed IR drop. At that time, I mentioned that when a catalyst is modified on the working electrode, new resistance component enter at the interface between the catalyst and the electrode. Here, I will discuss this interface between the electrode and modified material, focusing on the contact between the catalyst and electrode. The interface between the electrode surface and substance can be divided into three types in terms of electron transfer event. The first is when a substrate is absorbed on the electrode surface and electron transfer is possible between the fixed substance species. This is well studied as self-assembled monolayers film. The second case is when the electrode surface is participated by coating with long alkyl chain groups to prevent electron transfer from the outside. The third is when the electrode surface is modified with electrocatalyst solid and electron transfer occurred between the modified catalyst and electrode. The catalyst modified are often nano-sized crystals or powders, and as shown here, many of them are in contact with electrode surface or catalytic grain boundaries, make the electron transfer route very complex. In that case, junction is in contact as a two-dimensional surface, as shown in the figures, can be realized by coating the catalyst on the surface after it has melted at the liquid state, liquefied. The resistance between the electrode and materials can be explained by this equivalent circuit by using the resistance and capacitors. First, I consider the contact between the electrode and self-assembled films on the electrode. In this case, the well-defined surface is possible between electrode and surface-attached materials, so the electron transfer may occur across the immobilized groups. It may mediate electron transfer between the immobilized catalyst and the solution species by catalytic way, or electron transfer may occur in a tunneling effect. When the alkyl chain becoming longer, the current becoming smaller, and participation occurred on the electrode by self-assembled monolayers. Now I consider resistance between different phase contact in a three-electrode system at the surface-modified catalyst systems. The catalyst is modified on the working electrode, and when the catalyst comes in contact with the solution, a catalytic reaction with the substrate occurred. the potential is controlled by the reference electrode and current flow between the counter electrode. In this case, there is resistance to electron transfer at the electrode surface. Between the working electrode and catalyst, the contact resistance is present. Catalyst is often semiconductors or solid catalyst with a low conductivity, so the materials it exhibit resistance. This is material resistance. Also, an electron double layer is formed between the catalyst and the solution, causing the resistance to transfer or charging ions. In addition, there is solution resistance between the catalyst and the counter electrode. The sum of these resistance and the potential difference between the electrode. When evaluating the activity of catalyst based on the current that flow when potentials are applied to the catalyst, it is necessary to evaluate only the electron transfer due to the reaction with the substrate on the catalytic surface. In general, solution resistance between the electrode and the solution was compensated as the IR drop. But in the case of modified catalysts on the electrode, in this case, the additional resistance are present. Therefore, overcompensation may occur by simple automatic compensations. Therefore, sometimes partial compensation is applied for the uncompensated resistance. Various methods have been proposed for modified electrocatalyst on the electrode. As a catalyst support electrode, it must be conductive and catalytically inert. Carbon materials such as glassy carbon or graphite papers are often used. Methods of modification on the electrode include in situ growth by hydrothermal synthesis, chemical or physical deposition, and drop casting, a suspension of the catalyst, a solid on the electrode surface, is used. The shape and morphology of the catalyst on the electrode surface and possible charge transfer pathway are shown in this figure. The charge pathway for electrode coated with spherical nanoparticles for multi-layer composite membrane film, and for the electrode with catalyst on the support are shown, and the electron transport pathway is shown in the red line. Here I would like to present how to evaluate the performance of oxygen evolution reaction OER catalyst for the standardized of electrocatalyst based on this paper. To quantitatively evaluate the activity of the catalyst, it is necessary to know how the catalyst is prepared and its completion and solid phases. It is also important to investigate the conductivity of the catalyst when it is fixed on the electrode surface. For the electric cell, the working electrode should be gold or platinum or glassy carbon. For OER reaction, alkaline media is often used, so mercury oxide reference electrode is often used. The counter electrode is made of platinum mesh and should be larger than the working electrode. The cell should be made of plastic container such as PTFE to prevent contamination of the metal dissolution, because the metal ion impurity on the catalyst affects the catalytic activity drastically, and the electrolyte should be 1 molar potassium hydroxide. The uncompensated resistance of electrode and catalyst is then measured using the AC impedance method, EIS. Here is the example of equivalent circuit. The Nike's plot and board plot for measurement are used. This photo shows the measurement cell and also the QCM chip with the gold electrode is also shown on the right-hand side. This plot shows how the uncompensated resistance varied with the distance between the working and reference electrode. X-axis is the reference to working electrode distance, and y-axis is RU values. As distance increased, RU also increased. The brown and the blue plot dot indicate with catalyst and without catalyst filament. There is no significant difference between two. Next, I will discuss how to fabricate OER catalyst on the electrode surface. There are two major methods. The first one is the spin casting method. In this case, metal nitrate are dissolving in water ethanol mixtures. The addition of ethanol lowers the surface tension onto the electrode, which improves adhesion of the metal salt to the surface. The temperature is then heated to 150 degrees and then increased to 300 degrees to further decompose the nitrate ions. This result in a metal oxide formed. When the electrode, this metal oxide electrode is immersed in a 1 molar potassium hydroxide solution, it becomes hydroxide surface. The other method is electrode deposition. In this method, nitrate ions are reduced in water to form ammonium ion and hydroxide ions, and the pH increased in the vicinity of the electrode, which electrode deposit hydroxide crystals on the electrode. Here a cyclic Boltzmann on nickel, cobalt, manganese, and iron hydroxide electrode deposit film in 1 molar potassium hydroxide. The rising current on the higher potential side in Cb is a catalytic current due to the oxidation decomposition of water, and the sharp reversible oxidation wave, as shown here, nickel and cobalt, is the metal oxidation state change from 2 plus to 3 plus. When the electrocatalyst operating by injecting a charge into the electrocatalyst, the oxidation state of the metal changed. I investigate how this charge injection affects the conductivities of the catalyst by examining the conductivity of the catalyst. The system used here is interdigitating array microelectrode IDA as shown here. The conductivity is measured by depositing the catalyst on the surface of electrode and applying the small potential difference between WE1 and WE2 and measuring the current flow between two. Here is the cyclic botanogram of the cobalt hydroxide film and corresponding change in conductivity as the black line. When cobalt is 3 plus, the conductivity is good, but when cobalt is reduced to cobalt 2 plus, it becomes insulators. Conductivity as a function of potential is plotted here for the other metal hydroxides, which showing that cobalt and nickel are good conductors in the higher oxidation state, while iron and manganese is not a good conductors. However, when examines OER activity, we see that iron exhibit very high catalytic activity as shown here as the black line. It has been thought that iron is not good catalyst in the bulk solid state. However, it turned out to be very active in the thin film state. Iron-doped nickel or cobalt hydroxide modified electrode were prepared by the electrode deposition method, and the CV change by varying the iron amount X are shown here. In the CV, the current lies at higher potential regions arise from the OER catalytic reactions. Before the catalytic waves, we can see the prep peak associated with the oxidation of metal ions. When the doping amount of iron increased, this peak was oxidation reaction from the nickel to nickel 3 or cobalt 2 plus to cobalt 3 plus is shifted to the high potential directions. This shift indicates the electronically delocalized energy band exists doping by ions. It is important to know whether all the modified electrocatalyst solids are electroactive or not. The deposit amount of the catalyst on the electrode was obtained from the QCM measurement, and from the CV peak areas, the amount of the charge, which corresponds to the amount of the electroactive catalyst, can be estimated. Plotting the relationship between the QCM result versus the charge amount from the CV is shown here. The scan rate is 1 millivolt per second to 100 millivolt per second. By increasing the scan rate, the charge amount from the CV peak becoming smaller than the amount obtained from the QCM. This indicates electroinactive zone exists on the electrode surface. This means kinetically charged or ion transport becoming slow and insulating regions exist on the electrocatalyst. In the case of electrocatalyst, it is necessary to consider the contact resistance between the electrode and catalyst, such as the conduction resistance within the catalyst also considered. As a case study, I will show you several research examples. First example is OER active platinum, ruthenium, iridium ternary particle system supported on titanium oxide, and their resistance was studied in detail using electrochemical impedance measurements. Here is a SEM image. The actual catalyst is observed to have 10 micrometers dispersed grain on its surface. For electrochemical impedance spectroscopy data, they assume the spherical particle packing as a hexagonal lattice with the contact resistance. That is the resistance between electrode and catalyst particles and resistance within the catalyst particles, and also resistance particle and catalyst and solution resistance. These many resistances were considered to be connected as the transmission line circuit as shown here. The obtained EIS plot as a Nyquist plot is shown here. This experimental EIS result was simulated by the transmission line circuit models. From the simulation, the resistance value were obtained as shown here. The carbon and catalyst contact resistance is 100 ohm range. The next example is hydrogen evolution reaction catalyst on molybdenum sulfide, which has poor conductors. As a real catalyst, carbon is mixed with the molybdenum sulfide. Let's consider the charge transport on the molybdenum sulfide carbon electrocatalyst. First, when molybdenum sulfide is mixed with the conductive carbon, the electrode resistance is initially 200 ohms without carbon. However, as the amount of carbon added increased, the resistance decreased to 1 ohm as shown in this slide. The HER activities increased as the overpotential decreasing up to the carbon amount is 0.2, but which is saturated over 0.2. This is the 3 models for electron transport between electrode and molybdenum sulfide particles. The blue circle is a case where the molybdenum sulfide received electron from the electrode and reduced to the solution interface. The second model is the particle has a different activity itself. The particle from the longer distance from the electrode surface, the resistance is higher. As a result, lower activity as shown here as a white circle. The third model is the mixture between two, where there is a high contact resistance between the carbon and molybdenum sulfide, as well as the electron conduction from the electrode as the interface between catalyst and molybdenum sulfide. The electrons transport is examined by the rotating disk electrode. The experimental IV plot shows the change of taper slope with increasing the carbon amount, which indicates the resistance of the catalytic increase as the carbon increase. Therefore, this third model can be explained the experimental data. That is, there's some site that the electrode inactive because its high contact resistance between the carbon and molybdenum sulfide. Heterogeneous catalysts often undergo structure transformation when they operate under electrochemical reaction conditions. These transformations are reflected in their evolving catalytic activities. So there are several transformations can be considered. Example, morphological transformation, spatial distribution change, crystal packing change, aggregation or deaggregation on a support, change in the metal support interface, migration catalyst site across the surface, and give the new environment. Such transformation can be possible during the electrolysis, so we should consider it. And this transformation can be change resistance in the electrode, so we should be careful. Here again, the potential drop for the modified electrocatalyst measurement. The solution distance between the electrode and the solution will compensate as the IR drop. However, in the case of modified catalyst on the electrode, the additional resistance exists, as mentioned today. So, to evaluate catalytic activities, we should be careful for the overcompensations. Here is a summary of today's talk. The resistance in a modified electrocatalyst should be considered carefully, which affected the IR compensations. As a resistance, the contact between electrode and catalyst, catalysis support, catalysis itself, catalysis solution also considered. Resistance of electrocatalysts were sometimes changed by applied potentials through phase transitions. This may induce the resistance change. Therefore, several resistance measurements are recommended not only before the experiment, but also the experimental in progress. Partial IR compensation, therefore, is recommended for a modified electrocatalyst. Here is today's reference. So please read carefully and get on the informations. This is the end of today's seminars. Thank you for listening.
Thank you, Professor Haga. If you have any question regarding to the lecture, you can contact us. The next webinar, the Professor Haga's last lecture from this series, for the moment, we are planning to schedule for the beginning of December. The detail will be updated in the beginning of next month in the ALS website. For today, thank you and have a nice week.